And our first speaker is Jan Peters. He's a full professor in the computer science department of at TU Darmstadt. And since 2022, he's also the department head of the research department on systems AI for robot learning at the German Research Center for AI. He has received many honors, including the Dick Volt Best 2007 PhD Thesis Runner-Up Award, the RSS Early Career Spotlight, the INNS Young Investigator Award, and also the IEEE RAS Early Career Award, as well as numerous Best Paper Awards. He's an IEEE Fellow, an ELLIS Fellow, and an AAIA Fellow. Please join me in welcoming Jan.
Right. Good morning, everybody. As this is ICRA 40, I'll start with a video, and this video is actually even older than ICRA. It's 55 years old. That was right when the first robots started, that Unimate became so cocky, they said, we'll put robots into people's homes. Now, you'll see in a second that this was supposed to be sci-fi at the moment, but the engineering here is pretty much with what all of us grew up with, right? I mean, we all know how to program such a monster, and the methods are the textbook methods all of us have learned basically by today. Back then, they were very pioneering. Now, what is kind of sad, though, is when you go to Coral these days, the conference on robot learning, you feel every single video looks precisely like this, but just typically with a Franca or in simulation. So it feels a bit awkward to realize that we are 55 years behind the time. And well, obviously, the time started very differently, right? We started with the analytical robotics age. In the analytical robotics age, well, we had we believed that accurate models alone would be doing things very well because we know physics actually works, and there's pretty amazing ways to build simulator and models with the physics. Unfortunately, all models are wrong, and only some are useful. And we have all realized that just as modeling by hand is typically not efficient, not doable for all the possible scenarios. Then we saw that planning by itself, again, is actually pretty hard. And, well, that together with the fact of fast feedback control solved back then our problems. Now, when we talked about learning, in these days of the analytical robotics age, well, we typically directly were told off, oh, we'll never need you learning guys. That was literally what a German robotics professor from Stuttgart told me. And that's not even so long ago. That was just 15 years ago. Now, since then, a lot has happened. These are just some outtakes from even the pre-deep learning area, robot learning, which we did. So you see a little bit of reinforcement learning at a human child speed of learning ball in the cup. You see some behavioral cloning for ball bouncing task. You see behavioral cloning for bimanual manipulation. And finally, a mixture of behavioral cloning and reinforcement learning for robot table tennis. And, well, I think they're pretty nice tasks. And even before deep learning, we actually managed to do such kind of tasks. Now, since then, the world has changed big time. We've entered the black box big data deep learning age, however you want to call it. And as roboticists, we should feel highly uncomfortable with this. On the one hand, it gives us something which is very, very powerful, highly flexible representations with suitable algorithms. But unfortunately, we already know, well, physics stays on the way, so we get physically implausible solutions where our robots break for unnecessary reasons. We get huge optimization biases where the robot tries to optimize things which physically don't exist. And, well, finally, we don't actually understand the solution at all. So, also with a big down part. Now, Ken already said a lot about data. We have few episodes. On the other hand, we want to act and learn in real time. So we need a fast state action stream. And, well, we want to do this learning in the real world. And that means real damages, yes, and doing what the machine learning people always tell us, oh, just use a simulator. Well, then we could have solved everything with the analytical era approaches, we would never need learning if we can solve everything with a simulator. And finally, I think we all agree, you'll just ask your students if you don't agree, we all need loads of computation already, and we'll never have this on board in real time on the real robot. So for that reason, I think what we do need is a chimera of both eras. Now that may sound a lot like Ken, just that it comes from a very different angle, since we are actually asking, how should we best get to a chimera? And the answer here comes actually from machine learning. And, well, there's a wonderful quote. In inductive, that we want to have a robotics inductive bias, and an inductive bias allows a learning solution, a learning algorithm to prioritize one solution or interpretation over another, independent of the observed data. Inductive biases can express assumptions about either the data-generating process or the space of solutions. So it's not just the question of how can we do good old engineering, but much rather, how can we actually find in robotics these key insights which have made the robot engineer strong and try to bring them to learning algorithms? And how can we use them to build much better learning algorithms? And that should really be the goal of robot learning. So one thing, of course, is you really want to have the right kind of learning algorithms that measure proximity between policies in the right space. This is work of my PhD student Kai Plöger, and he has promised me I'll see 17 balls someday, since that's the physical limit. But the key insight is regularization of policy improvement by policy proximity allows us to really get very effective policy updates. Oops, now that is too fast. Then what you see, I don't know why this doesn't, oh, it does play. Okay, so this here is work by Puze Zelu, and Puze actually had a really, really cool insight. He controls the direction of exploration during the learning process. And I don't know why that movie plays so badly, but I'm pretty sure most professors, actually none of the professors and most of the grad students can't play air hockey that well. And the exploration here was directed in such a way that it doesn't harm the physical constraints. And he created a principled framework to bring the inductive bias of using your constraints to direct your exploration into learning systems. Finally, Rome wasn't built in a day, so quite clearly we need to figure out how to build the right curriculum for learning, as indicated here by these trajectories. And that video isn't so that now the robot is being started, and initially it just has to learn how to balance, and then later how to follow that trajectory. And by being given a learning curriculum, it can, and increasing the task complexity incrementally and controlling it by the learning performance, you can actually do on-robot learning. Finally, now, if you want to, we've done a lot of table tennis over the years. I got out of that 2 years ago, but this was the last results which we did with my PhD student Dieter Büchler, where we also built a robot, where we said our goal should be to have the robot which could do the nicest accelerations and then use exploration in the way you would want to do it for a muscle-based system. So really modulate it the right way on the muscles and use the natural dynamics of the robot to let that guide your learning process. And that allowed Dieter to walk out of the room and learn from scratch and come back 14 hours later to see this performance. Finally, well, we are all excited about what LLMs give us, and obviously they can now give us answers for many groups by just saying, oh, well, we give it some sentence and it will prepare the task. But how do you make this safely that this actually works out? Well, for that, you need another inductive bias. You need the inductive bias of bringing in policy representations, where policies are activated in a modular fashion, and where the policies are just then activated if they're physically plausible. And that gives us the last inductive bias, that we need to enforce physics compatibility in policies in order to make VLM, LLM-based task planning safe. With that, I would like to thank you for your attention. I wish this was me 40 years ago. It's my twice twins. But we only had PCs back then. And I hope you still have a few questions left.
Thank you. So we can take some questions while we change the speakers over. Can't actually. Looks like we have a question. Oh, there's one there in the kind of the wave your hand. Is that Omnon? Yeah, wave your hand.
So you talked about inductive biases of dynamics and physics and so on. But if you're going to train a neural network, and it's a fully connected neural network with ReLU activations, what about the inductive bias that comes from that model?
Oh, you mean how we could interpret these, or that we should?
How do you put those inductive biases that you're talking about
Okay,
in the model?
I'll give you a simple example of what we did. So Michael Luther, one of my PhD students, he created the so-called Lagrangian neural networks, which later kicked off the Newtonian and the Hamiltonian neural networks. And he basically chose the structure in such a way that he took a generic deep network and allowed it put these together so that it could only learn things which were physically consistent with the Lagrangian physics. The same thing he and some other of my PhD students like Joe Watson, pulled off by putting a differentiable Newton-Euler algorithm, again, with the learned elements in such a way that it can only learn physics plausible solutions. And with that, you can learn within 4 minutes of data things as complex as ball in the cup without having seen the task a single time. Okay, I think I'm getting kicked off. Oh, no, sorry, that was a...
Can we have another
Stefano.
question? Yeah, we need to get a mic there, though.
Yes.
Wave again.
Jan, very nice talk. Your words reminded me of a very old system, which was called CMAC, which was computer cerebellar something, in which the structure of the Lagrange equation were exploited so that you can learn only on the configuration space Q, because you know that the Coriolis and centrifugal terms are quadratic in velocity, and there's a linear acceleration. So you're exploiting in your network the structure of the equation. Is something like that you did?
So that is, for example, two things apart. So CMAC was an approximation of the cerebellum by using a hash table to create features. It was the pioneering work at cerebellar research and in robotics and machine learning. Now, what we did is we actually tried to create the right structure so that you would have automatically always a Lagrangian in addition to a solution of the Lagrangian, so that you can get an energy model out of it, a forward model, an inverse model, and that you could get energy-based control, for example, right away out of it. That was the example I just explained. That's one of the ways of how you can use physics in order to do control with a neural network in a way that you have safety and you have a solution which you can understand, which is physics-based. But it's only one of about 32 examples we have.
Okay, well, let's give Jan another hand. Thank you.
Right. Good to see you.